Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the concept of fields. It's an abstract definition. But before we get into that, let us recap what we did the last time. So the last time we defined rational numbers. Basically we made precise what we mean by rational numbers, and we just formalized the notion of rational numbers as we are familiar from high school. So what we did was we defined this set, basically all pairs of integers where the second guy is not allowed to be 0, and we defined an equivalence relation on it via this via this writing. And the equivalence classes were defined to be rational numbers, and the equivalence class of a pair was written in this way. And then we saw that one can also define an ordering on the set Q. So Q is the set of all these equivalence classes, the set of all the rational numbers. So the ordering was defined via this equation. Not an equation, via this by fiat via this in writing. So we observed that this is a total order, and that's that. And then an important point was that we identified the set of all the integers as the subset of the rationals, where an integer m was identified with this rational number, just as we used to do in high school. And we also noted that this identification respects the algebraic properties, meaning if you sum two things in integers and then take the image of the sum, or what you could do is you could first take the image of the individual things and then sum them. It doesn't make a difference. So that is respecting the algebraic properties. Similarly for multiplication, this is addition. Similarly for multiplication, and it also respects the ordering. So if m is less than m prime, then their images have the same order relation in the rationals. So basically, the rationals extend the integers in this way. And one thing I should have mentioned the last time is that the rational numbers is the natural extension of the integers, such that you can solve these kinds of equations. You cannot solve these equations in integers. For instance, 2x plus 1 equals 0 has no solution in integers. There is no integer x for which this is satisfied. But in rational numbers, you can solve all of these equations. So that is one perspective to construct rational numbers. So just like from naturals, we got the integers when we wanted to solve these kinds of equations. Similarly, we get from integers to rationals when we want to solve a little bit more general class of equations. So if you try to forcefully build a system which extends the integers, in which you can solve all of these equations, you will inevitably come up with what we did to define rational numbers. Alright, so now let us get into the material of this lecture. So we will be defining an abstract object, but we should supplement our understanding of abstract objects via examples, and I will mention what is the example that we should have in mind as we go along. So let us write the formal definition. So a field is the triple f plus and dot, where f is a set. So f is a set. This plus is actually a function of this sort, and the dot is also a function of the same sort. So do not confuse this plus with your usual plus as we use in natural numbers or rational numbers. This is just an abstractification of those pluses, if you will. And we somewhat confusingly, if you're seeing it for the first time, somewhat confusingly use the same symbol. So do not confuse this with the plus of natural numbers. So this plus we also call addition. This function is called the addition function. and this is called the multiplication of the field. And I would also want to add that instead of writing plus a comma b, we write a plus b. And instead of writing dot a comma b, we write a dot b, or just simply ab. We don't even write the dot. So this is just a matter of notation. And of course, there's a good reason for this notation. Nobody would be happy with this notation because of the kind of thing we are trying to capture. So let's see what are we trying to do. So of course, right now we haven't said anything. We just said that, okay, this is a triple where the first guy is a set, the second guy is a function of this sort, the third guy is a function of this sort, such that some properties are satisfied. So such that the first property that should be satisfied is associativity, meaning a plus b plus c equals a plus b plus c. And same for multiplication. So a dot b dot c equals a dot b dot c. And this should be for all a, b, c in F. Okay, so basically the point is that if you add two numbers and then add a third number here, what have I written? Sorry, I made a mistake here. What I wanted to write was this. So the point is that you can add the last two numbers first and then add the resultant to the first number, or you could add the first two numbers first and then add the resultant to the third number, just as we do in usual arithmetic. So this now we are demanding as an axiom. This is not something that, of course, one can prove, there is nothing to prove here. We're just defining something abstract. And same property should be satisfied for multiplication, just as it is satisfied in the multiplication of natural numbers or rational numbers. All right. And the second property is commutativity, which is that a plus b equals b plus a, and ab equals ba. Again, for all a, b, c in F. So that's one more property that we mimic from our natural numbers or integers or whatever. And this one is multiplicative and additive identity. So what we insist is that there exists an element in F which we write as 0, such that a plus 0 is a for all a in F. So let me write it in a separate line. There exists 0 in F such that a plus 0 is a for all a in F, and there exists 1 in F such that 1 dot a equals a for all a in F. So again, do not confuse this 0 with the 0 of natural numbers or rational numbers or any such thing. It's just a symbol which behaves just like the 0 of integers or rationals or whatever. So we just use the same symbol. And yeah, so that's that. And similarly for this guy. So we just demand by axiom that such things exist in our set, in this set F, which behave this way with respect to addition and multiplication. Alright, and this is called the additive identity, and this is called the multiplicative identity. And now for the additive and multiplicative inverses. So what we demand is that for all members in the field, there is some a prime, or let me write b, there is some b in F such that a plus b is 0, and the other is that for all non-zero. So this is also called 0. This is pronounced 0. So for all non-zero members of the field, or rather for f, there is some member such that AB equals 1. Okay, and a bit of notation, this we usually denote as f star. Okay. So that's that. And lastly, we have distributivity. So the addition and multiplication, right? So far they are just sort of behaving independently, but the next axiom relates them. So for all A, B, and C in F, we have A dot B plus C is AB plus AC. So the addition and multiplication, they behave well with each other. Okay, so these are some bunch of axioms, and yeah, for the first time if you see this kind of definition, it is a little bit jarring at what the hell is happening, but very soon one gets comfortable with these things. Okay, and here I should mention some remarks. So I want to say that this guy is unique. So meaning the axiom only demands that there is one such thing, but what I want to say is that there is only one such thing. So if, let's say, if 0 and 0 prime in F were both additive identities, meaning were such that, or are such that 0 plus, or rather I should say A plus 0 equals A and A plus 0 prime equals A for all A, then I want to say that 0 is equal to 0 prime. And how do we do that? So 0 plus 0 prime would equal to 0, because this you can think of as A. Sorry, what am I saying? This you can think of as A and use this equation. So 0 plus 0 prime equals 0. So that's what you get via this equation. But by commutativity, you get that this is also equal to 0 prime, because the left hand side is 0 prime plus 0, and now you can think of 0 prime as A, and therefore you get that 0 equals 0 prime. So this guy is unique. Similarly, you can prove that this guy is also unique. So there's a unique multiplicative identity and there's a unique additive identity. Okay, and similarly I want to say that given any element in F, there is a unique B in F such that this is 0. So let me argue that here. So if B and B prime are such that A plus B equals 0 and A plus B prime equals 0, then we want to say that B equals B prime. So what we do is, from the second equation, what we have is A plus B prime plus B equals B, but we can use commutativity and we get that this holds. But this guy is 0 via the first equation, and 0 plus anything is the same thing. So what this gives us is that B prime equals B. So therefore, there is only one such B for which this holds given any A. So this is called the additive inverse of A, because it is unique. We can use the definite article, and it is for this reason that we denote it by, so this is something that we denote by minus A. Okay, that's the notation. And similarly, you can show that the multiplicative identity is also unique. Given any non-zero element, there is only one b such that this happens by the same kind of reasoning. So this is something that we denote by a to the power minus 1, or we also use 1 upon a, whichever we like. All right. So that's the matter of notation. And what else do I want to say? Okay. Fine. Let us note one thing. So I want to say that minus 1. So let me put it as a note. So this is note. So what is minus 1? Minus 1 is the additive inverse of 1, which exists via this axiom. And suppose I multiply that by any element of the field. I want to say that this is the additive inverse of A. So one should realize that there is something to be proved here. This is the additive inverse of 1, and we multiply that with A, and we are saying that that is equal to the additive inverse of A. And for that we will use distributivity. So what we have is, for the proof, it's very simple. It's just 1 minus 1, or let me write A dot 1 minus 1 is A dot 0. Okay, before I say this, I should say something else. So wait a minute. So let us note something else first. So what I want to note is that A dot 0 is 0 for all A. Why is that? So this is because A dot 0 is A dot 0 plus 0, which is by distributivity A dot 0 plus A dot 0. And now whatever is this element, add the additive inverse of it to both sides of this equation. So what I'm saying is, this implies that A dot 0 equals A dot 0 plus A dot 0. And now if we add the additive inverse of this guy and call that additive inverse B, then what we get is A dot 0 plus B equals A dot 0 plus A dot 0 plus B. So if B is the additive inverse of A dot 0, then this is 0 and this is 0. So what we get is that 0 equals A dot 0 plus 0, but now by the property of 0 we have this holds. So again, this is all behaving in the same way as things behave in rational numbers. Alright, and now we note the second thing. So now I want to say that if we multiply minus 1 with A, we get the additive inverse of A. And the reason is that A dot 1 minus 1 is A dot 0 equals 0, which implies that A dot 1 plus. Okay, so I should not write it this way. It's not completely proper at this point. But I want to say that A dot 1 plus the additive inverse of 1. So far I haven't said what it means to write A minus B. A minus B simply means A plus minus B. So where minus B is the additive inverse of B, and we are just adding the two things. As such, there is no minus operation here. You can't subtract two things. So it's an emergent operation coming out of the field axioms, that you can take additive inverses and then you can essentially subtract things. But as such, it's not there in the field axioms. So that's why. But very soon we'll start making use of this. Anyway, so we have this guy equals A dot 0 equals 0, which gives us A dot 1 plus A dot minus 1 equals 0, which means, by the fact that 1 has the property that it doesn't disturb anything, it is the multiplicative identity. And this one I will write as minus 1 dot A by commutativity, which gives us 0, and therefore minus 1 dot A is the additive inverse of A. Because if we add the additive inverse to this side and that side, the right hand side becomes that, and the left hand side this and the additive inverse together cancel out to give 0. So what you're left with is that, and therefore we have this equation. So we proved this fact. Okay, so these are some basic properties, and one should always supplement such a definition by examples. Right now, the only example of a field that I can give is the field of rational numbers. So note that. So here is an exercise. Very important to do this exercise. That Q with its addition and with its multiplication that we discussed is a field. Well, let me make one comment that a field, what is a field philosophically? It is basically an object which allows for addition, multiplication, subtraction, and division. You can't do that like something like that in integers. You can multiply, you can add, you can subtract, but you can't divide. You can't divide two integers and get an integer. So its field is just an arena where division is also allowed. And we make that precise via a set of axioms that we discussed. And that's basically the message. It looks complicated, it is not. So yeah, and so basically just verify all these axioms that we listed above for this particular object. And this is our motivating example of a field for now anyway. Okay, and lastly, let me just make that notation precise. So we write A minus B to mean A plus minus B. Okay. Okay, so that's about fields, and now we want to discuss the notion of an ordered field. So an ordered field is a pair F, comma, the symbol, where F is a field and this guy is a total order on F such that something happens. But before that I need to say something. So when I say F is a field, well, I am being somewhat economical, because there is no such thing as F is a field. I should really say that F plus dot is a field, but nobody does this. This is for brevity, and this is encouraged because otherwise things become cumbersome. So when we say F is a field, there is some plus and there is some dot which we just hide from notations, and this will be a common practice throughout. So here, as we defined, well, a field is a triple blah blah blah, but we just simply write F and understand that there is a plus and there is a dot hidden from view. Alright, so what are the axioms this time? So two axioms. So one is that if whenever A less than B, we have A plus C less than B plus C for all C in F. So what this means is that suppose you have two elements in F such that the first one is strictly smaller than the second one, meaning the first one is not equal to the second one, and this holds. So as we noted in the lecture on relations, that this symbol simply means that A is less than equal to B and A is not equal to B. Okay, so basically what the first axiom says is that this order relation respects addition, just like, rational numbers or natural numbers. And the second one is that if you have this, then AC is less than equal to BC for all C which satisfied this. So again, what does this mean? This just is another way to say this. So I hope that is understood. So when we write A greater than or equal to B, what we mean is that B less than or equal to A, because this symbol as such is not legitimate. We only have the symbol, but we extend the meaning by this. We extend the meanings in a natural way. So there shouldn't be any confusion about that. Okay, so these are the two axioms that we insist on an ordered field. I should have highlighted my definitions earlier. Did I do that? I did not. Okay, so now another definition: the set P of all those elements where this is satisfied is called the set of positive elements of F. So we are already given an ordered field, and we call this set the set of positive elements, and we say P union 0 is the set of all non-negative elements, and this set, let me use the notation N, this is the set of all those members which are less than 0, is the set of all negative. Just some very simple definitions: positive, negative, and non-negative. Alright. And now a bunch of properties that are obvious. I mean, those properties should hold, but we need to prove them. So the first one is that if A is greater than 0, then minus A is less than 0. Why is that? This is because A is greater than 0 implies, by the first axiom, that A minus A is greater than minus A, which implies 0 is greater than minus A. And 0 is greater than minus A is precisely this. So we have that. Another note is if A and B are positive, then their sum is also positive. Again, very simple. It's just that A is positive implies, by the first axiom, but B is also positive, and by now transitivity of ordering, we get that A plus B is positive. Okay, and now another one is that if A less than B, then minus A is greater than minus B, which happens because if B is greater than A, which is the first one, it implies that B minus A is greater than 0. This is because of the first axiom. We are just adding the additive inverse of A on both sides, which implies minus A is greater than minus B, because now we are adding the additive inverse of B on both sides. So that's it. That's what the second thing was. That's what we wanted to show. Similarly, we have another one. Is that if A and B are both negative, then their product is positive. So this one is because this implies that this happens as we noted here, just like this one. Well, it's the opposite of that, so you can prove that if a less than 0, then minus a is greater than 0. It's just exactly the same thing. So if these both are negative, then these both are positive, and therefore minus a times minus b is positive by the second axiom, and minus a times minus b is nothing but ab. I did not show this, but you can show this very easily, because all you need to do is, maybe I should, so minus a times minus b is, as we noted, it is minus 1 times a times minus 1 times b, which is minus 1 times minus 1 ab. So all we need to do is show that minus 1 times minus 1 is 1, but that is because minus 1 times minus 1 is the additive inverse of minus 1. We show that minus 1 times anything is the additive inverse of that thing. So minus 1 times minus 1 has to be 1, because the additive inverse of minus 1 is 1. So that's that. I mean, if you didn't follow, then you can think of your own proof, but I've given all the details. So that's that. And now for another, this one is an exercise. It follows from the previous thing. So if a is negative but b is positive, then ab is negative. This is an exercise. And suppose a is non-zero, then its square is positive. So why is that? So if a is non-zero, then okay, fine. So there are two possibilities. If either a is greater than 0 or a is less than 0, it cannot be anything else. So if a is greater than 0, then a times a is greater than 0. That's simply because of the second axiom. This one. So that's not a problem. If a is less than 0, then minus a is greater than 0, and hence minus a square is greater than 0, but minus a square is a square. So that's one way to show it. All right. Another one is 1 is greater than 0, and this is the consequence of the previous one, because 1 square equals 1, and as we just noted something, if you square something, it is always positive, provided it is not equal to 0. But this is not equal to 0, you can easily show. Okay, so maybe I should build that in the axiom, because otherwise there is degenerate field. So let me build that in the axiom that 1 is not equal to 0. This is axiomatically assumed. So therefore, since 1 is not equal to 0, its square has to be positive, but this square is itself, and therefore you have this. Okay, and this is the last one, is that if a is greater than 0, then the multiplicative inverse of a is also greater than 0. And the reason is, if suppose by way of contradiction that this is the case, then as we argued above, that a product of a positive and a negative thing is negative, therefore a inverse is negative, implies 1 is negative, but that's a contradiction, because we already just showed that 1 is positive. So we have that. So all of these properties are familiar for natural numbers, and that is all that we abstracted out, the ordered field properties. Okay, and I should give these two exercises. So first exercise is that check Q with its usual ordering, which we discussed in the last lecture and the recapping of the last lecture, is an ordered field. You just have to check the two axioms. And the other exercise is that suppose f is an ordered field. Now again, so when I say f is an ordered field, there is an addition, there's a multiplication, and there's an ordering. So let f be an ordered field. So I'm suppressing all those notations. So when I say f is an ordered field, I mean this is a field and this is an ordered field, but all of that I'm suppressing, and everybody does that. So the exercise is that suppose you take two elements a and b, which are non-negative, in f, then three things: a less than b if and only if this happens, and I need to explain this notation. I will in a moment. A equals b if and only if a to the n equals b to the n, and this one is a greater than b if and only if a n greater than b to the n for all. This is for any, then for, okay, let me write it in the beginning. Then for any natural number this happens, but then what do I mean by a to the n? So a to the n simply means, so a square simply means a times a, and a cube simply means a times a times a, and similarly you can figure out what is a to the n. So that's just a notation. Okay, so I think that's all. Let me check. Yeah, that's all. So as usual, like, comment, share, subscribe. I also have a Patreon. The link is in the description below. Thank you for listening, and I will see you next time.